Okay, so good evening, everyone, and I welcome you all to today's live session of the course Nonlinear Vibration NOC24 me54. And This is an extra session, though we have completed all the 12 live sessions corresponding to the 12-week course of nonlinear vibration. But this is an extra session which has been scheduled in order to give a revision about what we have studied about the course. And So I'll be discussing about what we have been learning since the last 12 weeks. So, yes. Okay. Okay. So this course is being taught by Professor S.K. Dwivedi of IIT Guwahati, and I'm Rashia Aditi Ranjan, and I'm a NPTEL PMRF TA, and also I'm a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. Coming on to the overviews of the course that we have been learning. Okay. So the first thing that comes into mind is that what is nonlinear vibration? Why non-linear vibration, and what is the difference between mechanical vibrations and non-linear vibrations? Like we all learn mechanical vibrations in our bachelor's courses, which in which we talk about the vibrations, how it happens, how do we model a vibrating system, what are the cases that are there in case of a vibrating system, and everything. We discuss about it very thoroughly in mechanical vibration. But if we have been learning that course of mechanical vibration, then what is the need to study nonlinear vibration, right? So if we talk about mechanical vibration, firstly, so mechanical vibration is a okay. So in case of vibrations, what do we do? Well, the best thing that we are good at doing is we consider a spring, we have a mass, spring of stiffness K, and sometimes we also consider damper, a dashpot of damping coefficient C, and sometimes we also have some kind of a forcing here. Okay. So this is the case, and we have been studying many iterations of these kind of a system with 2 degree of freedom. Like this is a single degree of freedom system. We study about the 2 degree of freedom system, wherein we have two masses, two springs, two dashpots, and then we can have both the systems are being forced, or any one of them are being forced, and the other one is just like that. Many options we could learn, right? But in all these cases, what we consider is that our mass is concentrated at a point, then our stiffness is linear in nature. When I say linear, I mean is that the spring force is given as K into X, where X is my deformation of the spring, right? So, and likewise, we assume that my force due to the presence of the dashpot is also C into X dot. So, all these things, where here we assume that a system is a linear system, right? Linear system means that the variation of my input and output is linear, right? So, which means is that there exists a monotonic relation. Like, for example, if I keep increasing the stiffness, then my equilibrium state at which the mass, the weight of the mass and the spring force are going to balance itself. Now, if I keep increasing my stiffness, the deflection is going to decrease, correct? So there is going to be a monotonic relation, a linear relation. Like for increasing spring stiffness, the deflection is going to decrease. Okay, there's a monotonic relation. Likewise, it may happen that in some case, by increasing some parameter, the output is going to only increase, again monotonic. So, in case of a monotonic relation, it is easier for us to model. But if we talk about the real life applications and the real life problems, in that case, it is not necessary that we are going to have a linear system, right? Like for example, we all have pencil or pen. So the mechanical pencil or the pen which has spring in it. So if you'll take out that spring and try to conduct an experiment, you'll realize that when you start applying a force on that spring in order to compress it, initially it will be very easy for you to apply the force and compress it. But after some time, you'll realize that it becomes difficult. Further variation of the spring force, which leads to the deflection of the spring, it becomes difficult, right, with the variation of the deformation. So why is that? What is the reason that this happens? So the reason is, yeah, so the reason is that this happens due to the presence of the nonlinearity in the system, right? So it is very important that we consider the nonlinear effect into the modeling so that we'll be able to get a more accurate solution for the system, right? However, for a spring also, if I consider a certain range of the deformation of the spring, a very small range, it is going to behave linearly. Okay, but that comes with a condition that the range should be small. But what if I am having some oscillations which are happening at a very high amplitude? Then, then I cannot neglect in that case the nonlinearity of the system. Like for example, if I talk about elastomers, the elastomers have the capability to stretch to about like 100% of its length, right? So I cannot expect, and that is not even possible, that it stretches to twice of its length, and then it is behaving linearly. That is not possible. It is definitely going to operate in the nonlinear zone. So it is very essential that we consider the nonlinearities of the system properties and take it into our modeling equation so that we'll be able to know that how my system is going to behave. But now I have a linear system. I have a linear differential equation. I can solve the linear differential equation in order to get the solution. But now, since I have a nonlinear system, solving a nonlinear system is a very difficult task. Okay, and that we'll talk about that in the further slides. Okay, so first thing is that we learned about how to identify the nonlinear system. So if you people remember, we learned about a superposition rule wherein if my system satisfies the superposition rule, then I say that my system is linear, otherwise it is non-linear. So if you remember my superposition rule, okay, Sachin, I am just going through whatever I have taught you people since the last 12 weeks. If in any case you have some doubts or some questions that you want me to answer, you can ask me anytime. Okay?
Sure, madam.
Okay. So superposition rule. So if you remember, superposition rule had two rules, right? One was the additive rule, right? So additive rule said that, for example, if my function is f1, which gives me a solution x1, and if there is function f2, which gives me a solution x2, then f1 plus f2 together should give me x1 plus x2. So what do you have to do? Like for example, if you have a nonlinear equation, so you just put the value in it and then see what you are getting as a solution. Okay. Values as in variables. Like for example, if I have a system like x double dot plus kx plus k1x cube is equals to 0, and I want to know whether it is linear or non-linear. So do one thing, assume this as f. So if you put x1 in it, you'll get f1. If you put x2 in it, like in place of x, then you'll get f2. And then when you will replace x by x1 plus x2, then what you get, if it is equal to f1 plus f2, then your system is linear, otherwise it is non-linear. Anyways, it is not going to satisfy the superposition rule because it is a non-linear system. Okay. And I hope that after learning this course, you people must have developed an intuitive understanding that by only seeing the equation, you could tell that, okay, my equation is nonlinear. Okay, and the second one was your homogeneity rule. Homogeneity rule and homogeneity property, wherein you had like if your f gives you x1, sorry, f gives you x, then your alpha f should give you alpha x. This also you can do. What do you have to do? You'll have to replace x by alpha x, and then you can see whether your solution is equal to alpha f or not. Okay. And this will be applicable for vice versa also. Since in this case, my x is the input, I would say is it is the independent variable, so I can check it with that also. Okay. Now coming on to soft and hard spring. So if you people remember, we learned that springs are essentially not linear. However, if we operate it in a certain zone, it is going to behave in a linear fashion. However, springs are non-linear, and the non-linear spring are essentially of two types: soft and hard. Soft and hard depending upon how does the force varies along with the deformation. So my linear spring, if this is my spring force and this is my x, which is the spring deformation, my linear spring is something like this, right? A linear relation. And the slope is going to give me the stiffness of the spring, right? So this is my linear spring. Then I have two cases wherein the behavior diverges. Okay, so this is my soft spring and this is my hard spring. Okay, so soft spring means that after a certain value of like your x, it becomes really easy to deform the material, right? Like if you see here that, yeah, it becomes really easy. While in case of hard spring, it is very difficult. Like if you see over here that after this, the force that is required, if I talk about here, the force for this amount of deformation, the force that is required, it is very less because the line is almost horizontal. Okay, so the force that is required to further deform the spring from some position A to B, it is very less. So that is why we call it linear, soft spring, because with the increase of x, the force that is required to further increase the deformation is actually less. And with the, in case of the hard spring, the opposite is true, which means that with the increase of x, the force that is required for the further deformation increases very abruptly because you can see that the curve tends to go to the slope of infinity, right? So if you see over here that for a small variation of x, the force that is required is significant. Now, if I'll go in the upper phase, it increases a lot. Okay, so then we have a soft spring and a hard spring, and in case of a soft spring, I can write the spring force as k x minus k1 x cube, while in case of a hard spring, I can write this as k dash x plus k1 dash x cube. Just for example, that usually it is of this form because if you'll see that with the increase of x in these first two terms, like only the two terms are there, with the increase of x, if you'll see, the x cube is going to dominate, right? X cube is going to dominate. So the negative part is going to increase, right? So that is why it is a soft spring. While in case of your hard spring, the x cube dominates and it adds to the force, right? So this is your soft and hard spring concept. After that, we learned about superharmonics and subharmonics. So if you people remember that when we talked about super and subharmonics, we learned that it occurs in case of a nonlinear system, right? Now, why does it occur? So I even solved an example to make you understand that from where does the sub and superharmonic terms come. And if you have any confusion, you can definitely go to that lecture. It was probably in week one or week two. No, it was in week one live session. I discussed a question wherein after applying the harmonic balance method, I showed you that how the terms of sub and superharmonic are coming into play. So when we talk about subharmonic and superharmonic, what does it mean? So it means that in case of a subharmonic, firstly, if I talk about the characteristic, so in case of my linear system, if here is the amplitude and here is the frequency, the behavior is going to be something like this, right? In case of nonlinear system, what is going to happen? This is going to divert something like this or like this, depending upon whether my system is softening or hardening. Okay. Apart from that, if I take very small vibrations, this is for a linear. Apart from this, if I consider very small amount of vibrations, okay, by very small amount I mean in the linear range, I would say. Okay, so in the linear range, somewhat, if I consider the vibration, you'll notice that in case of a nonlinear system, apart from having a peak at the resonant frequency, we can also have a small peak over here and a small peak over here. And you'll realize that if my this is omega, then my this is some n times of omega, and this is omega by n. Now, this is what essentially gives us an idea about the sub and super harmonics. So, in case of a linear system, there is only one peak, okay, at the frequency, where the frequency could be the forcing frequency if my system is damped, and it is going to be the natural frequency if my system is undamped and it is not being and it is not under some periodic excitation. However, in case of a non-linear system, despite having the same kind of a system, when you plot the amplitude frequency response, you will get to know that there are occurrence of multiple peaks. Okay, and those multiple peaks are because of the nonlinearity present in the system. And these peaks are at some multiple of omega, or it is something like omega by n. Okay, there is some integral value that is being divided with the omega principal frequency, or which is being multiplied by omega. Okay, so these gives us the idea about sub and super harmonic. Okay, so if I have to characterize that which one is the which case, so if you remember, I told you that don't go towards the frequency variation. You first have to consider the time period. Okay, so for example, my time period is given as 2 pi by omega, correct? Now, in case of subharmonic, what is going to happen? So when it is sub means my time period is going to decrease. Okay, intuitively we can understand that, okay, if it is subharmonic, it may happen that the omega is being divided by some integral number, not integral, I should say, positive integer. So in case of subharmonic, your time period actually gets divided by some value. Okay, so in that case, your subharmonic could be written as the case where your t dash is t by n, or your omega dash is equals to n times of omega. This is your subharmonic, which means if a peak appears at some integer multiple of omega, then we say that subharmonic is there. While in case of superharmonic, we had t dash is equals to n times of t. So my time period was actually getting multiplied by some positive integer. So my omega dash was now omega by n. So these two were my cases for sub and super harmonic. Okay. And after you'll solve certain problems, and you'll get to know that if there is x cube, cubic nonlinearity, then in that case, n is equals to 3 could be seen. If I have a square term of x, like x square, then n is equals to 2 could be seen. Okay, coming on to other things, quasi-periodic response. So in case of a quasi-periodic response, we characterize that a system will have a quasi-periodic response when there are two frequencies present in the system such that those two frequencies are incommensurable, or the ratio of these two frequencies are irrational. For example, omega 1 by omega 2 is going to be irrational. And for example, I can take omega 1 by omega 2 is equals to under root 2 or under root 11, something like this. Okay, so these two frequencies are incommensurable, then my response is quasi-periodic, and my quasi-periodic response is different from periodic response because in this case, the dominant frequencies are actually incommensurable. And if you remember that in phase plot, my quasi-periodic response can be seen by a torus, right? There was this example that there are two concentric circles and the behavior could be seen something like this. But this is a typical example that I'm giving you. The quasi-periodic response could be seen in different ways also. However, it is going to be something like that of a torus. But the best way to see whether the response is quasi-periodic or not is by analyzing the frequencies that are being present in the system. Okay. Then we'll talk about the behavior of 2D equations. Okay. So if you remember that in case of 2D equations, I gave you an idea that if my system is linear and it has two dimensions, like if I have two equations, x dot is equals to something and my y dot is equals to something, then in that case, if I want to know whether my system is stable or not, or if I want to find the solution, what I could do, so for a 2 degree of freedom system, if I have two solutions, if I know any two solutions, then in that case, I can write the general solution uh, by writing the linear combination of those two solutions, right? And I gave you the analogy that for a two-dimensional plane, if I have one x-axis, if I have one y-axis, so if I want to express some point like 3 comma 4, how would I write it in vector form? So we know that universally it has been defined that I take a unit vector I in x axis and a unit vector j in the y axis, and likewise I can write any point 3 comma 4 as 3i plus 4j. Correct? So what did I do? I had two independent coordinates, two independent vectors, and I wrote some other vector in that plane in terms of those two vectors. It's a linear combination of those two vectors. The similar analogy is for a two-dimensional system also. So if I have two equations, linear equations, and like of this form, like my x dot is f of x comma y. Then in this case, if I want to find the solution, so if I get any two solutions, then I can write the general solution as the linear combination of those two solutions. Okay, first thing. Second thing, what if I want to know about the stability of the solution? Or what if I want to know about the stability of the fixed point that are present in the system? So first thing was to find the fixed point. How do you find the fixed point? You'll put x dot is equals to 0, you'll put y dot is equals to 0, and then you'll get the equation from which you can find the fixed point. First thing. Second thing, that what about the stability? So if you remember that we could write this something like this, x dot is equals to a into x. We could write x dot is equals to a into x, where my x dot was just what? This, and my capital X was x and y, and my a was something like A, B, C, D, a matrix. Okay. So if you remember that I talked about eigen values and eigen vectors, right? So eigenvectors is essentially those two directions wherein the solution becomes independent of the second direction, right? In case of eigenvalues, my system is transformed in such a way such that my two equations they decouple itself, right? They get decoupled, and then I can find the two independent solutions, and I can just find the linear combination and write the solution. Okay, so how do I find eigenvalues? How do I find eigenvectors? So then we talk about eigenvalues. So you know, for a matrix A, I can find out the eigen values. How? By finding the determinant of A minus lambda I. So eigenvalue by finding the determinant of what? A minus lambda I, I'll get a this is equal to 0. I'll get what? I'll get a characteristic equation. From the characteristic equation, I can get the eigenvalues, and from the eigenvalues, I can find the corresponding eigenvectors. Okay. However, if I get the eigenvalues for eigenvectors, I'll have to find the eigenvectors if I want to know that what is the solution. But if I want to comment on just the stability, then I can just find out the eigenvalues and then I can talk about the stability. Because if you remember that after I found out the eigenvalues, my solution was given in such way. My like x was something like uh, x1 cos, or let's not assume cos, it would depend, e to the power lambda 1 t plus x2 e to the power lambda 2 t. Do you remember? The solution was something like this. So, depending upon whether my lambda 1 and lambda 2 are positive, negative, or imaginary, I can tell whether my system is stable, unstable, asymptotically stable, or periodic, everything, right? So, from here you can see it's an exponential function. If lambda 1 and lambda 2 are both negative, then what? My system is stable. Definitely, because at time tends to 0, what is going to happen? It is going to approach 0. And let us assume for now that my 0, comma 0 is my fixed point. Okay. Then after that, if I talk about lambda 1 and lambda 2 are both positive, then my system is unstable. Sorry. Then my system is unstable, because if you see that when the time increments with time, as time goes to infinity, my system is going to go to infinity. So definitely it is not stable, it is unstable, right? And then if I talk about if my lambda 1 is negative and lambda 2 is positive. So if you remember that in this case, my fixed point was a saddle, right? Now by saddle, what do I mean? By saddle, I mean that in one direction it is positive, while in the other direction it is negative, which means though my system would try to approach the fixed point from a direction, however, as it tries to reach the fixed point, the second direction is going to take it to infinity. Remember, I also discussed a question wherein I plotted the phase plot in order to show that how the saddle is going to behave, because you can see it from the equation of capital X also. This also let us assume it at x solution. This also, from this equation you can see that if your one lambda 1 is going to be positive and the other lambda 2 is going to be negative, so at time would go to infinity, your one value is going to come to 0, but the second one is going to go to infinity. Correct? So that was the case of your saddle. Then comes the case when your lambda 1 and lambda 2 are imaginary. So in case of imaginary, there were also three cases, right? Lambda 1 are imaginary. And there were further three cases. First, when real part of lambda 1 is equal to real part of lambda 2 is equal to 0. In this case, what was the solution? Well, in this case, my system was showing periodic response. Okay, it will show periodic response. So wherever for the any initial condition, if I'll start give it my system an initial condition, it is going to just keep rotating. Just it will keep rotating with the same amplitude. Okay, periodic. While when my real part of lambda 1 and real part of lambda 2 is what? Positive, what is going to happen? In this case, my system is going to have a spiral out behavior. Spiral out, it will keep spiraling and then will go to infinity. Remember, because you see that in that case your solution is going to have some components of cos and sine. Along with that, it is going to have some positive exponential values also. The positive exponential is going to increase to infinity with time when t tends to infinity, and your cos and sine is going to result in the circular kind of a motion. So it would spiral out. And third case, when your real part of lambda 1 and real part of lambda 2 both are negative, in this case, your system is going to have spiral in behavior. Right. Likewise, we discussed and we concluded that okay, this is how you are going to tell about whether my system is stable or not. However, whatever I told you for this stability analysis, it was for what? It was for linear equation. Yes, Sachin, do you have any question?
Madam, is spiraling considered as a stable system? Can we consider spiraling?
You can say it's a stable system. However, it's a asymptotically stable system, if I talk very precisely. Okay, because when we talk about asymptotically stable system, we say that my system is going to attain the fixed point at t tends to infinity, correct? Now, my e to the power something negative into time is going to go to zero when? When my t tends to infinity, right? For t10 or t20 or t30, it is going to have some small value. It is never going to go to zero, right? So that is why it is stable, but precisely if I talk, it's an asymptotically stable system. Understood?
Yes, madam. Thank you.
However, it would again depend upon the value of lambda. Now, if my value of lambda is 500 or 600, in that case, it is going to settle very soon. Okay.
Madam, one doubt.
Yes.
That periodic response we can call it as stable. First case you explained, madam.
See,
Real part is zero and imaginary part is there. That case
yes,
it will be having a periodic response. In phase
yes,
portrait it will be a circle,
yes, yes, yes.
and that we can call it as stable, and whatever spiral in we can call it as asymptotically stable. Isn't it correct?
A periodic response, see, periodic response is not actually, uh, you can say, stable response. Now, you would ask me why? Because in periodic response, well, like when we define the response as stable, we say that if I take my system and take it to some place and then I leave it, if it comes back to that point, then my system is stable. Correct?
Ah,
In
yes,
case
madam.
of periodic response, if I take my system to some point, you will realize that it is never going to come back to the stable point, correct?
Ah, yes, but it is bounded, right?
Yes, so we call it marginally stable. That is
Okay,
why we call it marginally stable because it is bounded, however, it is not reaching the stable point or like my fixed point. So we call it
yes,
marginally stable because if you'll see that it's a boundary condition, right?
yes.
If I try to plot it this like if this is my real case and this is my imaginary, so in case of this for this, the point should be something over here, right? So it lies on the boundary, so it's a boundary condition, right? So we call it not stable but marginally stable, but anyways it is going to be a part of stable, but it is not properly stable. Okay.
Okay, thank you.
Okay. Okay, so whatever I discussed about the stability, it is for what? It is for a linear system, right? But we are dealing with nonlinear system. So what do we do? So as I have told you earlier also that there is no specific formula or theory which tells me about the stability of a nonlinear system because a nonlinear system is very difficult to deal with, right? So what do we do? So what I do is for a nonlinear system, I'll first find my fixed points, right? In that case, my system would be something like x dot is equals to f3 x comma y and y dot is equals to f4 x comma y, right? And in this case, these both are nonlinear. So by solving on myself or by using the numerical method that you people have been taught, like if you remember that we discussed about the Newton-Raphson method and bisection method by which we were able to get the roots of a particular equation, of a nonlinear equation or the equation that we're having transcendental function and everything. So first, what will I do? I'll find the fixed point, and then what am I going to do? I will now linearize my system about that fixed point in order to know whether that fixed point is stable or not stable. Okay, so what were we doing? We were defining the Jacobian matrix, if you remember. So we defined our Jacobian matrix as delta F3, yeah, partial differential with respect to x, partial differential or f4 with respect to y, and we had partial differential of sorry, 3, f4 with respect to x and partial differential of f4 with respect to y. This is how we define the Jacobian matrix. After that, we'll put x comma y is equal to whatever fixed point I want. For example, if I have 3 fixed point, 4 fixed point, 5 fixed point, however, how many amount of fixed point we have, we'll have to deal with them one by one. Okay, so I'll just find the Jacobian equation. I'll put the value of the fixed point, then I'll get a linearized matrix, and after that, I'm going to find the eigenvalues. Now, then I'll find eigenvalue of Jacobian matrix in order to know the stability of the fixed point. Okay, so Sachin is asking, is Jacobian used only for nonlinear system or it can be used with linear also? No, there is no point of using Jacobian matrix for linear system. Okay, Jacobian matrix is essentially a matrix which is used to linearize a nonlinear system about a point. Like if you people have like you must have studied mathematics, so there we have Taylor series and Maclaurin series. Remember, so in series and Maclaurin series, what do? We linearize the system about a point, right? So similarly, Jacobian is basically used in order to get a linearized system about a fixed point. So definitely for a linear system, we don't need Jacobian because a linear system is already linearized. It is easy to deal with a linear system. I have proper theories. I know how to deal with a linear system. I know how to find the solution of the linear system. However, Jacobian is used to linearize the system and know what the equation is going to be close to the fixed points, and then I can find the solution for that range of value. Okay, I hope that I answer your question. Like if this is my fixed point, for this range, I'll linearize. Okay. So now also you can ask me that why do I need to linearize when my equation is nonlinear? So sometimes you know that if I don't go into the complicated dynamics, I want my system to be at a stable point and the perturbation or any kind of a wind that my system is getting through or any kind of behavior forces that my system is experiencing, it may happen that it is very small. So in that case, I can use Jacobian. I can linearize the system and find the solution, and then I can get the proper solution of the equation. Okay, now what was the last thing? Yeah, behavior of 2D equation. I guess this one is done. So coming on to the next one, where we discussed about derivation of nonlinear equation of motion. So we discussed about how would we derive the equation of motion, because as an engineer, I know how a physical system is. I can see how a physical system is. I may intuitively understand that how my physical system is going to behave. However, if I want to know that how my system is going to behave, I need to have a mathematical mapping between the physical system and how I'm going to model the system. So in order to model the system, it is very important that we know that how do we find the nonlinear equation of motion, right? Then only we can predict how the system is going to behave. So we discussed the ways of equation of motion. Apart from that, there are two more things. For example, if I have a system, like uh, if I talk about what? If I talk about uh, maybe a scale, and if I try to bend a scale, right? So how could I model it? So for a scale, if you see that my scale is a continuous body, it has a distributed mass, right? So how would I model it? I cannot consider it as a lumped mass. Can I? How can I assume that okay, my all mass of the scale is concentrated at a point? Then whatever, if I am like taking a scale and trying to bend it, can it happen if I consider that the mass is concentrated at a point? That is not possible. The only thing that can be done with that mass is that it can oscillate or maybe rotate, or it can just perform some kinematic operations. I cannot bend it and everything. So how will I model it? So I will have to model it in some other way, right? But now how would I model it? So what I can do is that maybe I can consider four masses that are attached by a thread, and then they can bend like this. Right, I can assume that, or I can consider that it is a continuous distributed mass and then I model the equation. It depends on me and on the application as well, right? It would depend upon what kind of application I'm using the system in, right? So depending upon that, as if I am an engineer and if I want to model a system, I would first see that how its behavior is, whether it is oscillating in one direction or whether it is oscillating in two directions. Like in case of a beam, if I see, then how many degrees of freedom does it have? Here is a scale. I try to bend it. Firstly, it's a 2D object, so definitely it is having two motions, right? Likewise, if I consider, let us say this bottle, I'm trying to move it from here to here. What is happening? How many degrees of freedom? Well, this bottle has 6 degrees of freedom. It can translate in three directions. It can rotate in three directions, right? And so it has a 6 degree of freedom system, right? Same is the case with the scale also because it's a free object. I can rotate it, I can translate it, anything, right? So, but if I constrained my system, okay, now by constraining it, what do I mean? I mean is that if I take this bottle, I hold it, or maybe I apply some welding equipment and I just keep that bottle in that, and it is always like this. So, how many degree of freedom does it have? Zero. Because now it cannot translate, it cannot rotate anything. Until and unless I'm not going to move my hand, it is not going to perform any kind of application on its own. Right. However, what I can do is I can apply a pressure like this on it so that it would translate. Right. So, and it can also rotate like this, 2 degrees of freedom. So what do I realize? I realize that if I constrained my system, I decreased its degree of freedom from 6 to 2. What does this mean? This means that now initially my system was having 6 degrees of freedom. So if I try to model it with a spring mass system, I would have six masses. Then only I can maybe think of modeling it. But now it has only two degrees of freedom. So two masses can do my work. I'm talking about the hypothetical case. Okay, so two masses, or if I consider only the translation motion. Okay, in that case, initially my bottle was having three translation motion. Now it is having only one translation motion. So only one mass, if I consider my bottle, this bottle as a mass, a spring and a dashpot, then my work is done. Right. So depending upon the application and depending upon how my system is behaving, I can model it as what? As a lumped parameter model or a distributed mass model. So in my lumped parameter model, I'm going to have some n degree of freedom corresponding to which I can get n equations of motions. And in the distributed mass, I have infinite degree of freedom. So it is very important that first I realize that what kind of a system do I have to make. After that, then I'll go into the deriving the equation of motion. Now, the equation of motion could be done by these four ways. The first one is your Newton's law. It is a very well-known law. What? Summation of all the forces is equal to mass into acceleration. This is what my Newton's law. Everyone knows it. It's a very simple law, and we learn it in the very initial days. Right. Now, when I talk about D'Alembert's principle, D'Alembert's principle is nothing but a extension of my Newton's law, because here what we do, we actually take a equivalent, static equivalent of my dynamic system. Matlab, simple. I'll just take my MA on the left hand side and write it equal to 0. Now, what does this mean? This is something like a dynamic system because it is having some acceleration. Now, I consider that, okay, my mass into acceleration is also an integral part of all the forces that are being applied. So now it becomes a static equivalent of the dynamic case. Static equivalent of dynamic case, right? Now, in this, we'll have to apply the force balance. And if you remember, where we also did many questions wherein we discussed about that how to find the equation of motion for a linear system, for a non-linear system. If you remember that for a spring mass system, we consider the 2 degree of freedom system, and we discussed that, okay, for a linear system, I find the equation of motion, and then after that, I can add on the non-linearity by replacing, like for example, if I had a non-linear spring, for finding the equation of motion, I'll consider, okay, kx, and then after that, once I find the equation of motion, I'll just replace my kx with k11x plus k12x cube with the non-linear variation of the spring. Okay, that I think I have taken 2 3 questions for this, and I guess that thing should be clear to you all. Okay, apart from that, we have energy approaches also, wherein we have the Lagrange and extended Hamilton principle, wherein we first compute the kinetic energy and potential energy, and then we define the Lagrange as kinetic energy minus potential energy, and then we write the Lagrange equation as d by dt, partial differential of L with respect to qk dot, where qk dot is what? It is the first differential of my generalized coordinate. Now, firstly, what is a generalized coordinate? So, if the best example, consider the pendulum. Okay, so the what does the pendulum do? Okay, so I'll just explain. So this is my pendulum. So if you see that it is having some deflection in the x direction, and it is also having some deflection in the y direction. However, when we write the equation of motion of a pendulum, do we actually write it in terms of x or y? No, we write it in terms of theta, where theta is what? Theta is the angle this. Why? Because for a non-extensible thread by which my pendulum or the bob is attached to the fixed plane, what is happening? I can write my x and y in terms of theta if I know the length. L cos theta, L sin theta. So what did I do? I made my life easier, right? So I wrote the equation of motion in terms of theta so that I know what the theta is at any time t. Then I can just multiply it with L with the cos, and I'll know that what is my L cos theta and L sin theta, what is my x and y coordinates. So what did I do? I made my life easier. Instead of dealing with 2 differential equations, what did I do? I dealt with only one, right? So here qk is what? Your generalized coordinate. Like in case of pendulum, your theta is what? Your generalized coordinate. Your physical coordinate is x and y that you cannot disagree with. But you have a generalized coordinate which is theta, which could be used in order to compute x and y for any time t. Okay, so we try to define the generalized coordinate in order to make our life simple and the computation simple, right? Okay, so this was your Lagrange equation where L is your kinetic energy minus potential energy and Qk is your generalized force. Now you would ask me that what is generalized force? So for example, if I have a spring mass system and the mass is having is being applied by a forcing of sinusoidal nature, then QK will be equal to F sine omega t. Simple. Any external force that is acting on the system in the direction of the generalized coordinate is going to be my generalized force. Simple. Then similarly for extended Hermitian principle, what is it? It is used for the non-conservative system, right? So in case of a conservative system, I'll have a kinetic energy and have a potential energy, and the kinetic energy and potential energy is going to be what? It is going to have some interchange in between, but the total energy is always going to be the same because it's a conservative system. While in case of a non-conservative system, that is not the case. In the non-conservative system, because of the presence of the damping or friction, some energy will be lost. Some energy will be lost, right? So in that case, we used extended Hamilton principle, which says that we integrate from T1 to T2, what? Delta. Okay, kinetic and of kinetic energy minus potential energy plus delta W NC into dt is equals to 0. Okay, so here your WNC is what? The work done due to non-conservative force. Okay, and I've also taken an example in order to explain to you that how these things are going to work. So please go through those examples. It will be very helpful for you. Okay, so this is done. Now coming on to this. Okay, now comes the most difficult thing. Solution of the nonlinear equation of motion. Now we know that how do we find the equation of motion? How do we know that what the system is going to behave? Everything now we have realized. But now if I want to know the solution, which is essential also, because if I don't know the solution, how would I know that how my system is going to behave, right? So now if I want to know the solution, how it is going to happen. So first thing first is that my system is non-linear. So if my system is non-linear, what does it mean? That finding a closed form solution is difficult for me, right? Finding a closed form solution is difficult for me. So what would I do? Either I'll use the methods that has been considered up till now, like harmonic balance method, Lindstedt-Poincaré method, method of averaging, method of multiple scale, everything, right? And the lectures are also sufficient in order to make you understand that how these methods are. Like in case of harmonic balance method, what do? We consider the solution in terms of what? In terms of my series, Fourier series. And then what do? I consider those solution, I put it in the equation of motion, and then I try to find out the constant values of the solution that I assume so that I can find the solution, right? But what is the assumption? The assumption is that my solution is periodic, right? In case of Lindstedt-Poincaré method also, I do the same thing. I assume my solution in what form? If you remember that in case of Lindstedt-Poincaré method, I assume my solution as, sorry, x as x naught epsilon x1 epsilon square x2, something of this form, right? And after I assume this solution, what do? I put it in the equation of motion and then I try to separate the powers of epsilon. Like the epsilon to the power 0 terms are going to be equal to 0. The power of epsilon to the power 1 are going to be 0. And likewise, I'll get multiple equation and then I'll find the solution of the first equation, put it in the second equation, and likewise, then I'll try to remove the secular term and find the solution. This was for your direct expansion method. In case of Lindstedt-Poincaré, we add one more thing also. What? We write our omega also in terms of epsilon, like omega naught plus likewise. And everything is going to be the same. Then in case of method of averaging, also similar kind of a thing we do. In method of multiple scale, we define the slow time scale and the fast time scale, and then again we put it in the equation, try to separate the secular term, and then from there we'll get the values of the constant, and then we'll put it in the main equation and get the solution. However, in all these methods, we have an assumption. What assumption? Assumption that says that, okay, whatever happens, my solution is periodic. But as you have seen, as I have discussed, for many numerical techniques, is my solution always periodic? No. For a nonlinear system, it may happen that my solution may go to period doubling, or it may go to chaos or quasi-periodic. Right. So how to deal with those kind of a solutions? Although these methods are really good if you want to deal with for a small range of solution, right? So a small range of operation of your system, right? These are very good and these are going to help you. Anyways, when we deal with the numerical solution, there is also a thing that we do when we try to do research, like what I also do, that if I find a solution by numerical method, what happens is that it may happen that my numerical system has some error. So what do? I find the analytical solution by any of these methods, specifically multiple scale method. So by that I'll get an analytical solution. Sorry, by that I'll get an analytical solution. And then from the analytical solution, now if I compare my numerical solution, what do I know? Now I'll get to know that whether my numerical solution is correct or not. Right. So even if you want to work on the numerical solution only, it is very essential that you work on the analytical solution in order to know whether your numerical solution is correct or not. Okay. And I'll not be going into deep of these solutions because I have discussed it a lot in the live sessions. And I guess it is very clear. It is all mathematical and you'll have to deal with that. However, there's one thing that I would mention over here about the secular term, that why do we use the secular term and from where does it come? So if you remember that if I have a differential equation of the form like x double dot plus x is equals to sine of t, right? So you know this kind of a solution is going to have a complementary function in the particular integral. So anyways, whatever be the complementary solution, if I talk about the particular integral, so if you remember in this case for a particular integral, what do? We write sine of t, and then here we can write it like what? D square plus 1 into x. So here what do? We write d square plus 1 and then we replace d square by minus 1. So if you see, it will become sine of t by 0, which becomes undefined, which is not correct, right? So what do we do in that case? In that case, we multiply this by t into sine of t and then do whatever it is, whatever is done. However, what is important is the multiplication with t. As t tends to infinity, x tends to infinity, right? This is what is going to happen if I consider this as a part of my solution. So what do I do now? So what do I do in that case? In that case, what I do is I neglect this. I say that whatever the coefficient of this term is, should be 0 in order to have a stable solution. Okay, and that is the idea from where we get the variables of my solution. And all this idea is being used in all these three things. Okay, it is very important that you understand this. Okay, in case of harmonic balance method, it is a different case. And if I talk about the numerical solution, I've told you that what do you have to do? If you have a second order differential equation, then you will first convert it into two first order differential equations, put it into MATLAB, give it the parameter value, and the code. I have also shared the code in the PPTs, okay, in some initial PPTs. However, for the certain sessions, like I guess I don't remember, but the last sessions I've not shared the code in the PPT. The reason being that I've already shared it earlier also, and from that only you just have to change the function, and everything is going to be the same. Okay, so you just have to put the initial condition, and find out whether your system is going to be periodically, quasi-periodically. Apart from that, there's one more thing that I want to mention. What are the possible solutions of your nonlinear system? Very essential. It could be fixed point, periodic, quasi-periodic, chaotic. Now, if someone asks you that for the particular initial condition of the particular parameter value, what is going to be the solution, what will you do? You will first simulate the response. If it is a fixed point, it is going to be constant with time. If it is periodic, it is going to be circular, or maybe if it has experience period, doubling bifurcation, something like this, or it can also have three, something like this, anything. Then it is going to be periodic. Quasi-periodic, what? It is going to be something like a torus. Now, when I say something like torus, what I mean is that, see, it may happen that there are certain number of loops in your periodic solution also, right? However, in case of quasi-periodic system, you'll notice that not every time you're going to have such kind of behavior, but there is one very nice way to finding out that the phase plot is quasi-periodic or not, is when whatever the solution you'll get, whether it is having some kind of a band or not. Band, I mean that maybe you are going to get something like this. And when you'll zoom this area, you will see something, some convergence or something uh like this. Okay, this kind of a behavior. Usually these are seen in what? Quasi-periodic behavior. This is not seen in periodic behavior, right? In periodic, it may happen that due to numerical error, you could see that this is a very thick line. Instead of a thin line, it is a very thick line like this. Okay, like this. But then how do I know whether it is periodic or quasi-periodic? So when you zoom it, in case of periodic, you will see in the zoomed area that this is just like this band. There is no overlapping in case of periodic response. Okay, no overlapping. However, if there are overlapping, some crossing and everything, then it is what? Your quasi-periodic response. So that is the best way. However, this is also due to error. This is not a correct way of saying that it is a periodic response, but it may happen that due to some error, when you perform the simulation, it can happen. Okay. And for the chaotic, I've already told you how you can find out whether your response is chaotic or not. Take the initial condition, simulate it, apply hold on the figure, and then what you are going to do, change the initial condition. Like for example, if you have the initial condition x naught dot, change to x naught plus 10 to the power minus 4. No, butterfly type response is in a predefined shape. See how you're saying that it is in a predefined shape. I mean, there is no predefined shape that your quasi-periodic response should be of this type. It would have multiple shapes depending upon the your system, right? Butterfly effect was given the name butterfly effect because the shape was like that, and the essential reason that butterfly type response is known as the butterfly type response is the story that I told you of that of the butterfly effect. If you remember that a butterfly flocks its feather at one part of the earth, then it may cause a tornado on the other part of the world. However, it may happen that that flocking can also lead to the decrease of the tornado that has been happening on the other part of the earth, which means that a very small variation at this point of the space, which is not even significant, is going to cause such a big phenomena at the other part of the world. That is why it was known as chaotic and it was named as butterfly effect. And it is said that any chaotic response is having the characteristic of a butterfly effect. That is what I am telling you. That take this initial condition, simulate the response, then take this initial condition and then simulate. Then there can be two things. First, that the response, what does this mean? Not chaotic. It is not chaotic. If the response is same after some time, it is not chaotic. And if the response is same for some initial time but diverges after it, then it is your chaos. So as you asked that it has a predefined shape, so predefined shape is not the criteria for saying whether it is chaotic or quasi-periodic. This test is. Your butterfly effect is going to have this thing when you try to simulate it. For a very small variation of initial condition, it is going to show divergence after some time. And that is why we say that it is chaotic and it is not quasi-periodic. Also, there is certain other way. In case of quasi-periodic response, you have some finite number of frequencies. And in case of chaotic response, you are going to have a band of frequencies. Right. So as you said about the butterfly effect, so no, we cannot consider it as a quasi-periodic response because it's a chaotic response because for a small variation of initial condition, it is going to show a large variation. Apart from that, we have Lyapunov exponent also, which could be used to find whether the response is chaotic or non-chaotic. If it is the Lyapunov exponent comes out to be positive, my response is chaotic. If it comes out to be negative, my response is not chaotic. Okay. So first thing that you should do when you get a response should be like first try to know whether it is chaotic or non-chaotic. And once you get to know whether it is chaotic, your life becomes easier. And then if you see that your response is not chaotic, then you will have to find whether it is periodic, quasi-periodic, fixed point. Okay, okay, this is done. Coming on to,
Uh, excuse me, madam. One doubt is there in previous slide.
yes, tell me.
These methods you told it is applicable for periodic excitations. If I
Hmm.
give non-periodic excitations like random excitations or um, step excitations,
Mm-hmm.
whether still these methods will be applicable for finding the solution of nonlinear equation of motion.
No. You would ask me why? Because you know differential equations, linear differential, ordinary differential equations. You people must have learned it in your mathematics course, right?
Yes, ma'am.
So any kind of a forcing that satisfies my criteria, which can be used for finding the particular integral,
Hmm.
is given, then I can find the solution. However, if now I get a forcing that is not inside that linear criteria or by which I cannot find the solution or cannot find a particular integral, then this method fails. Then you'll have to go to the numerical method.
Okay, ma'am.
Understood? So it is
Yes.
very important that if you have the idea of ordinary differential equations, how to find the complementary function in particular integral. So for the particular integral, if the criteria is fulfilled, you can apply any of the method. If the criteria is not get fulfilled, then you'll have to switch to the numerical method. Or you can do one thing also. You can actually linearize your forcing. But then that will be a very specific case. However, you can linearize also. Like for example, we can write a sine of x in power form, right?
Yes.
Expansion form. Likewise, we have certain functions that we can write in that way. So you can use that. However, for that also you can consider only up to one term. So that will be applicable only for a very small range.
Yes, madam. Thank you.
Okay. Okay, so this I've already discussed, right? This is done. Phase plot of a system, you know, phase plot means x dot on the y-axis, x on the x-axis. This is your phase plot. For a periodic response, it is going to be like this. Okay, so this is going to be a phase plot. Jump up and jump down. So this comes from the your frequency response. So in case of a nonlinear system, we know that we are going to have something like this, a bend in the frequency response. So what is going to happen if I keep on increasing my omega for the system? I just started with 0 omega and now I start increasing my omega. So what is going to happen? My system is going to follow this path till here. After this, it does not have some place to go. So what will it do? It will not come here. No, it will jump from here to where? This point, and then we'll start following this. So this is known as your jump phenomena, and this occurs why? Because of the unstable part in the amplitude frequency response. Okay, similarly, if you'll start decreasing omega, it is going to follow something like this up to this point, and from here it is going to jump like this and then follow this. Okay, so and these things are studied in order to prevent any kind of a failure to the system. Okay, and this kind of a behavior can be seen only in your a nonlinear system, not in your linear system. Talking about the stability analysis. So stability analysis, I have already discussed that you define the Jacobian, then find the eigenvalues, and then you will know that whether the certain or whether particular fixed point is your stable, unstable, marginally stable, or whatever could be the solution possible. Okay, however, it is very important that you understand that the stability criteria is true for only very small range, and the system may get unstable if it goes out of that zone. Okay. And then in this course, we also discussed about some numerical techniques, like numerical techniques for finding the differentiation. And there is also a MATLAB command DIFF, which could be used for finding the differentiation. Then integration, we had I and T. Along with that, we have numerical techniques also, like for differentiation, we have Euler method. For integration, I have your Simpson's one-third rule, Simpson's 3/8 rule, trapezoidal rule, which can be used for finding the integration, because again these things I can do by MATLAB or by my hand up to certain level only, right? What if my system is very complex, some powers, positive powers, high positive and high negative powers on the the numerator, and high positive and high negative powers in the denominator? In that case, we prefer using what? Numerical techniques for differentiation and integration. Similar is for finding roots. Like I told you, that in order to find the fixed points, we take x naught and y naught is equals to 0, and then we get two equations which have x and y, that too in numerical non-linear equation. So when I have a non-linear equation, in that case, when I try to find out the root, it becomes very difficult for me. Like for example, if I have x plus sin x is equals to 0. Can I find it? Can I find the root on myself? No, I cannot. I cannot find the exact root. However, I can write it in a series form and then I can find the root, but then the series goes to infinite numbers. Right? I am going to consider only up to a finite number. And up to a finite number means that I can consider maybe up to 5, x to the power 5 or 6. Because above that, I don't even know that how can I compute the root of a algebraic equation above that power. Okay, so in these cases, what do? We prefer numerical values in order, numerical techniques in order to find the roots. Okay, so do I have to write down the methods or you people can do it? I think I've discussed it in the live session also, and it is being discussed in the lecture also. So I'll just skip it.
Excuse me, madam.
Yes.
Madam, in a previous slide, madam, in phase plot,
Hmm.
Suppose if we have two second order differential equations, and uh, and suppose in that two second order differential equation, if the x and y both terms are available. Suppose we have x double dot like first differential equation, and in that
Okay.
x and y both is there. Same way another is the y double dot differential equation, and in that also x and y both are available. So the
Okay.
phase plot will be x dot versus x, or it will be x y if it is a mix of x and y.
Then you're going to have two phase plots. One is going to be x dot and x, and other would be y dot and y. So if you plot x versus y, then that will not be your phase plot. That is what? That is your basically a plot that shows that how your both the axis or both the variables are actually changing. When we say phase plot, by phase plot I mean that for a particular variable, for a particular system's dynamic, how is my position and velocity varying? Okay, so for phase plot, one axis should be your position and the second should be the velocity of that particular position only. Understood? So in that case, which you are saying that if I have 2x double dot is some equation f1 x comma y, and I have y double dot is equals to f2 of x comma y, and here if someone tells you to show the place phase plot, then you are going to have two phase plot wherein one will be your x versus x dot, and the second versus is going to be your y versus y dot, because the phase plot is always between the position and the velocity.
Yes, thank you, madam. Got it.
Okay.
Madam, one doubt is there in this phase plot.
Yes.
Actually, two variables you told, madam, x versus x dot and y
Huh.
versus y dot.
Huh.
Is there any possibility like one system will be like behaving one way, other variable will be behaving other way? Like x dot may be behaving in uh, quasi quasi periodic, and other will be like periodic or fixed point. Is there any possibility like that, or both will be behaving in a similar way?
Mm. Both are possible. It may happen that it behaves in a similar way, and it may happen that it does not behave in a similar way. Right? Anything could happen. Specifically with a nonlinear system, it is definitely possible. Right? It may happen that one of your I'll tell you example of one of the problem that I am dealing with. I also have two equations. Both are like x double dot and y double dot kind of thing. And in that case, my one behavior is of beat phenomena and second one is periodic. So definitely this can happen.
Chaotic and periodic can mix like that.
Chaotic and periodic, yes, that can also happen. And I'll give you an example also for this that you consider maybe I don't remember this. It is Lorentz system only. Lorentz system, I've given you the example also. So I would tell you to study a bit about Lorentz system. You'll get to know that your Lorentz system is a three-dimensional system. Okay,
Yes.
and in that case, you'll see that there is in the chaotic region, you'll see that your two this Lyapunov exponents are positive and the third one is negative, which means that your chaos is happening only in the two direction while the third direction is non-chaotic. So definitely it can happen.
Okay, madam. Thank you.
Okay. Okay, types of damping, I guess this is not that much important. However, you know that we have Coulomb damping, viscous damping, and everything. And it is important while we are modeling the system. Usually, in the works that we have done till now, we have considered the viscous damping because we have considered the Rayleigh dissipative potential, or we can say that we have considered a damping as C into X dot. Okay, then we talk about the modal analysis, which is done for a linear system in order to find out the modes, or we can say in order to find out the natural frequency of the system. Since if we have two degree of freedom system C, we'll have two natural frequencies, right? So modal analysis is done in order to find those frequencies, and then corresponding to that, we can find the solution also. Or we can also find the range up to which we need to work on our system, right? And then comes the bifurcation. So we have discussed different kind of a bifurcation, like we have discussed the saddle node bifurcation. We discussed about the pitchfork bifurcation. Now, pitchfork bifurcations were further of two types, where there was supercritical pitchfork bifurcation, and then there was subcritical pitchfork bifurcation. And in both these bifurcation, what was seen is that either there was the three branches they were occurring, or there were either they were stable, they were unstable. Like in case of supercritical, we had one branch which was stable, and after the bifurcation, we had three branches, out of which the previous branch which extended became unstable, and then two new branches became stable. Sorry. And the opposite was seen in the subcritical pitchfork bifurcation. We had transcritical bifurcation, and all these were static bifurcations, right? Apart from that, we also learned about the dynamic bifurcation, like the Hop bifurcation. And the Hop bifurcation was further of two types, subcritical, supercritical. And then, if you remember, we also discussed the criteria in the mathematical form, that okay, if my this equation satisfies, then my this kind of a bifurcation is occurring. If my this is satisfying, this kind of bifurcation. Anyways, we have also discussed the normal form. If I remember, we have this, yes, we have discussed the normal form of the bifurcations. Like with examples, we discussed that how our system behavior was changing with the bifurcation, and how the parameter was playing the role. And then we had this critical bifurcation point. We were calling critical bifurcation point to a point wherein the bifurcation was actually happening, right? So these things were discussed, I guess. Okay. And after that, bifurcation. Do you have any questions regarding bifurcation?
Madam, regarding static versus dynamic bifurcation points, can you
Uh-huh.
give one example in static nonlinear system and one example in dynamic bifurcation?
Uh, Example, as in, like you want to know that where does it happen, like that?
No, madam. For example, Duffing equation, if we see frequency response, we will be having one particular point where um, static bifurcation is happening, like
Mm-hmm.
saddle node bifurcation.
Mm-hmm.
Similarly, for dynamic,
Mm-hmm.
the time response also will be coming into that, isn't it? Whether we can call like Matthew equation or Lorentz equation will be having this kind of bifurcation, dynamic bifurcation.
See, Lorentz equation. I don't remember. Though Lorentz equation have bifurcation, and it is it is your dynamic bifurcation. However, it is period doubling one. But if you are talking about bifurcation, then the best example is that we were discussing yesterday of the Duffing oscillator. You remember we were discussing that the how the amplitude was changing with frequency.
Yes, madam. Yes.
So that is the biggest example of a saddle node bifurcation in a dynamic system. However,
Yes.
if I remember, I've also taken some example of Hop bifurcation also. Yes, I remember. I have shown through numerical method also that how my dynamic Hop bifurcation was actually, yeah, actually Hop bifurcation is dynamic only. But since you have asked, so I guess saddle node bifurcation is the best example. So saddle node bifurcation could be seen in your this static case also and a dynamic case also. Now you would ask me how saddle node bifurcation is in dynamic and static. So see, if I
Yes, madam.
have my equation something like mx double dot plus k1x plus k2x cube plus, let us not take any plus, let us take it equal to 0 for now. Now see, here I have a parameter mass, right? Now if you see that my x is going to change if my mass change. isn't it?
Yes, madam.
Because I have a spring, I have a mass, and this spring is balancing my mg, correct? So for this case, if I consider, you see that I have x cube. So I have mg is equals to k1. Okay, this is the case where we neglect the the equilibrium state. So if I take the equilibrium state, it would be something like k2 x cube. This is my equation. Now, by seeing this equation, you know that there are going to be three roots of x naught, correct? Because x to the
Yes,
power
madam.
3 is there. So now see, if there are three roots, it may happen that if I take mass as a parameter and here I take x naught, it is going to have this kind of a behavior. It is also having a saddle node bifurcation. And generally we see it in like for the system that I work in, electroactive polymer, we have this kind of a bifurcation. When we basically deal with a polymer that has a voltage and we consider as a equilibrium stretch, or we can say equilibrium position. So in that case, we do have this kind of a behavior, you know. In this case, when we change the voltage, it happens that my system has the behavior is something like this. Okay, so here you can see here this. This part is my unstable equilibrium. So you know when I keep increasing, now my voltage is now my material is viscous, it is having damping in itself. Okay, so what is happening if I apply voltage, it would oscillate by some amount and then it would stabilize. Okay, but you'll see that if I keep increasing the voltage gradually I mean that first I gave it a voltage V1, then the system stabilized, then small amount of voltage is increased, then the system is given sometime it's stabilized. But as soon as it reaches this point, no, after this, even a very small variation in voltage leads my system over here, and then it follows this path. Okay, so here you can see a static saddle node bifurcation. Correct? I hope that you understand this. And if you even if you have doubt in this, I would suggest you that if you could see one of my research paper, in that I have explained it very thoroughly that how this is happening. And anyways, as you were asking the last day that if it is the upper point is stable, why do we call it unstable? Like, what is the reason? And
Yes,
how can it cause failure? So in my system, what happens is that this upper limit, I don't want my system to go to that upper limit, because if my system goes to this upper limit, now my system is going to burn itself. So that is why we always operate our system in only this zone. After that, we don't even operate our system, though it has a stable point above in the above area, but that is a dangerous zone. My system causes failure, so that is why we don't go over there. And as you said about the uh, as you said about the dynamic case, so as I discussed in the earlier class, if we have frequency and here if I have amplitude, in that case my system response should be something like mx double dot plus k1x plus k2x cube is equals to f sine omega t. In this case, your with the variation of frequency omega, you'll see some behavior like this. So this is your dynamic saddle node bifurcation. Now, why am I saying dynamic is because see, amplitude means my system is having a periodic response with some amplitude, right? So with the variation of frequency, the amplitude is changing. Okay, though only one thing, the amplitude is changing, but that amplitude is of a periodic response. Okay, so that is why we call it a dynamic bifurcation, which means that my dynamic characteristic of the system is changing with the parameter. In case of a static bifurcation, my static characteristic or the equilibrium point is changing with the parameter. Uh, is it clear
yes,
now?
madam. Now it's clear. I understood.
Okay. So where was I? This is done. Parametrically excited system, you people know what is a parametrically excited system. A system wherein my parameter is going to vary with time, that is my parametrically excited system. Like we have the Matthew equation. Okay, so I hope that there is no doubt you people can easily identify the parametrically excited system. Or should I say that if you have something, some equation is equals to f sine omega t, that is a forced system, externally excited system. While if you have something of Matthew equation kind of thing, or if you have something wherein your excitation is being multiplied with your x or x dot, then in that case you have a parametrically excited system. Simple, your parameter is varying with time. Okay, then resonance theory is basically related to the resonance characteristic, wherein we try to find out the resonance, like in case of a parametrically excited system, like in case of a externally forced system, we had resonance condition and then we had sub and superharmonic. Well, in case of parametrically excited system, we had two cases, right? Like we had the sum of the principal frequencies, and then we had the subtraction of the principal frequencies, and along with that we also had, I guess, the uh, just a second, yeah, that was the case as far as I remember. Yes, principal parametric resonance condition, yes, where we had the multiple of the, like if I have omega 1 and omega 2 for my parametrically excited system, then we had two cases, right? Principal parametric, wherein we had omega as twice of omega 1 or something like that, and then we have the combination, wherein we had omega as omega 1 plus minus omega 2, something of this kind. Okay, then we have the Floquet theory. Then, like for a the static case, I told you that you have to find the Jacobian and then you can find out whether your system is stable or unstable. But in case of your this periodic solution, like for example, if my system is having a periodic orbit, then if I give some perturbation from that periodic orbit, whether it is going to be stable or unstable. So for that, we studied about the Floquet theory, wherein we consider that my system is actually going through a periodic solution, and then we did the all the like analytical work, and then we got to know that I have to find out the value. Sorry. Then I wherein we had to find out the value lambda. From where do we get lambda, if you remember? So we have defined a matrix, and then we also defined a monodromy matrix from where we used to find out the value of lambda. And then depending upon the value of lambda, again we were predicting whether our system was stable or unstable. So in this case also we had that if my lambda was positive, my system would be unstable, and if my lambda is negative, my system is stable. And then we also defined a Floquet multiplier, wherein Floquet multiplier was such that my lambdas were brought inside to a unit circle. So if the lambda, the absolute value of lambda was inside the unit circle, then my system was stable. If it was outside the unit circle, then my system was unstable, if you remember this. Right. And there was one more, if I remember, criteria, that if my lambda was equal to 1 and lambda was equal to minus 1. So if my lambda was equal to 1, then at that time the period of my solution was t, and if my lambda was minus 1, then the period of my solution was 2t, if you remember, where t was what? T was the time period of parametric excitation. Okay, so this was about the Floquet theory. Then we had the case of limit cycle, existence of closed. Okay, so I talked a lot about this, your limit cycle. So there is a difference between your periodic orbit and your limit cycle, isn't it? Okay, so your periodic orbit is what? So if this is my x and this is my x dot, this is what my periodic orbit. Now, when I say periodic orbit, what I mean is that with the change of my initial condition, my amplitude is going to change. So my frequency is going to remain the same, but my amplitude is going to change. So this is my periodic solution, periodic orbit. In case of limit cycle, I have a cycle, this, and whatever initial condition I take, x dot, whatever initial condition I take, it is always going to take me to that point. So if I take this initial condition, it will spiral like this and then take me to the this orbit only. Or even if I'm out of this, it is going to take me there. So this is my limit cycle. Eventually, every periodic cycle that is present in the nature is essentially a limit cycle. Now, why do I say so? You know, beating of a heart, right? So my heart beats at a particular, if I consider it as a balloon or something like that, it beats at a particular amplitude, correct? What if I try to give some perturbation to the oscillation of my heart? Is the amplitude of oscillation of my heart going to change? No, it is going to again come to that particular value only. Why? Because it is a limit cycle oscillation. Whatever perturbation I try to give it, it is always going to follow its own path, right? Similarly, every periodic cycle that is present in the nature is generally limit cycle. Okay, then we discussed about the existence of closed orbit, and there were some criteria that were discussed. Then stability and bifurcation of periodic response, which was given by the basis of the Floquet theory. I guess we discussed some more questions in that week. And then we talked about chaos. And I guess now the idea of chaos is clear to you people. Check for the initial condition, variation of the initial condition. If the response is same after the certain period of time, then your response is not chaotic, otherwise it is chaotic. Okay, and this has already been done. Logistics maps were just considered in order to tell you about how does discrete time dynamical system change. So logistic map was essentially a prey-predator model which was shown to which was used to show that how your system actually your population growth is. Then we talked about Poincare map and Lyapunov exponent. So your Poincare map was what? So if you have a system, this is chaotic. So, though my system is chaotic, it is having some aperiodic motion. Why is it not going to infinity? There was this question that came into the researcher's mind, and then he talked that okay, if my response is not going to infinity, it is always bounded, then there must be some hidden pattern in my system. Right, in order to find out that hidden pattern, Poincare section was introduced. So, in case of Poincare section, what do? We decrease one dimension of my system. Now, when I say I decrease one dimension of my system, what do I mean? Like in case of a Lorentz system, I have X, Y, and Z. So what would I do? I would choose some value of Z. Let us say Z is equals to 4. Okay, so I'll choose this plane. Suppose I have a three-dimensional plot, I choose a plane. So whatever points of x and y that lie on that z plane, that I'm going to plot, and that is going to be my Poincare section. However, if I have a periodic excitation which is adding the third dimension to my system, like in case of a Duffing oscillator, you see that I have x double dot, which means two dimension, and the third dimension is being added because of the sine of omega t. Right. In that case, what do? I cut my section. At what points? At the points where omega t is equals to 2n pi at every time period. Or should I call it like this? If my t is the time period, so what would I do? Like for example, if I have x, I have x dot like this, and here I have time like 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, likewise. And then I have these values. Okay, so what do? After 0 to capital T, let us say it is over here. I'll take it and I'll plot it. Then I'll take over, sorry. Then I'll take this at 2t, plot it. Take at 3t, plot it. Likewise, I'll take up to n times of t. So this is what my Poincare section does. I decrease one of the dimension by just taking the points which are at the n times multiple of my time period. Okay. And if I talk about the Lyapunov exponent, so Lyapunov exponent essentially gives me the divergence, rate of divergence from a particular point. So what do? For example, if my initial condition is this x naught dot, and it is going over here, x1 dot. Okay, so what do? How do I find the divergence? I will give some small perturbation x naught plus delta x naught comma x naught dot, and it would lead to some x1 dash dot dash. Okay, so what would I do? Suppose that this distance is d and this distance is d naught. So ln of d by d naught, if it is positive, what does it mean? My system is diverging. If it is negative, then my system is converging, right? Because if my d is greater than d naught, it would be positive. If my d is less than d naught, it would be negative. So this is how, and then I just average this out with time, and then that gives me my what? Lyapunov exponent. Okay. So then we talked about the vibration reduction techniques, and okay, do you people have any question up till here, or in general any question?
Madam, in Pointer section,
Yes.
experimentally measured data when we were trying to find it.
Mm-hmm.
If it is a pure data, actually there will not be any issue. But usually experimental data will be having noise.
Yes.
So when we first, if we find FFT of that and find the largest frequency, that is the smallest time period, and
Mm-hmm.
if we um, section it with that time period,
Mm-hmm.
but usually the noise will be contributing, and we may not be exactly tell whether point care section is smooth or like due to
Yes.
noise it is coming or due
Yes.
to chaotic it is coming.
Yes.
So how
Yes.
to
Yes.
differentiate that?
So there is this windowing we do with this kind of a signal. However, I don't remember exactly about it. But what do? We define an interval. I would suggest you if you could read much about it. But I'll just tell you a brief about it. So we use a windowing function. So in that you said that if for a data, if we have noise, so what do? We define a window. Okay. So what do? For that window, we take the function and then we analyze it. And then after that, we try to remove the noise from it. However, if while you are taking experimental data, it is better that you use some kind of a filter. Are you not using any kind of a filter to remove the noise?
Yeah, we are using like anti-aliasing filter or low pass filter
Mm-hmm.
for removing more than certain frequency, but less than that frequency definitely some noise will be there.
Yes, yes, yes. And apart from that, it may happen that you'll have noise for a higher frequency also. You can have a noise for lower frequency also. That is why you use in windowing of the function. However, you are absolutely correct that with the noise, because there are many cases when our system response is actually periodic, but because of the noise, my system behaves chaotically, and people are not
Yes,
able to
ma'am.
identify whether it is periodic or chaotic.
Exactly.
So the best way is if your like filter is not able to do the required task. So signal processing, you'll have to study a bit about signal processing, that how would you reduce the noise from your system, and then how you would analyze the system. I guess windowing would do your work. Apart from that, as you told that you found out the uh, highest peak, right? For
Yes.
the like the lowest time period. Did you try to find out the natural frequency of the system?
No, madam, I don't know about physical system. I only have measurement data. With that data, I want to say my system is chaotic or um,
Okay,
periodic.
okay.
That was my objective. Actually, I didn't try any practical data since the sir was explaining in the class this method. I'm
Mm-hmm.
having this doubt whether how to deal with noise.
Yeah, yeah, yeah. So best is Yeah, so best way is windowing, you see, and you can also see some advanced signal processing techniques that are used to avoid noise, because noise is a very big reason that sometimes chaos is seen in the system. So you look into that because it's related to mostly signal processing technique,
Yes,
and
ma'am.
so I could not give you some expertise in that because I haven't worked much on the signal processing thing. But windowing is something that I have dealt with, and with because I remember that we used to superimpose some kind of a noise to our signal in order to find out the natural frequency. And so because of the noise, the natural frequency was not correct. So we were windowing our function, and after windowing, we were able to get the exact natural frequency of the system. So I guess that would be helpful for your work.
Yes, madam, I will try that. Thank you.
Okay. Okay. Any more questions?
No, madam. Thank you.
Okay, no, I'll just complete the slides, then you can leave. However, are you people going to give the exam or something? Have you registered for the exam?
Yes, madam. I have registered
Okay, when is your exam then?
on Sunday.
Okay, this Sunday.
Yes, madam.
Okay, how is your preparation going then?
Actually, I have completed 6 weeks till 6 week
Okay.
online sessions I have, and remaining are still pending. But I
Oh,
will try to complete it within 1 or 2 days.
yeah, yeah, yeah. If you'll complete it, it will be better for you. And if you have solved the assignment problems, then that will be also good because mostly if you will be able to solve the assignment problems, it will be easy for you to understand, right? So in just 5-10 minutes, I'll just complete my slides, then I'll just conclude the session. Okay. Apart from that, there's one more thing that I would like to tell you that if in any case after this course you have any doubts for me, so you can mail me at my email ID, and this is my email ID. I would be happy to answer your queries. Okay. So I'll just complete the slides and then you may leave. Okay, so after that, needs and type of vibration reduction techniques were introduced, and vibration reduction techniques, as I discussed also, that it was needed for some kind of a machines or some kind of environment wherein, like, if my machine was having a very strong motor, it may happen that because of the rotation of that motor, some kind of a vibration could be produced. Like, motors, they have, what if there is some eccentric loading? Because we cannot expect that a manufacturing process would give me an idle machine. So it may happen that there is some eccentricity because of which some kind of a vibration would get produced. And if I keep it in some laboratory or maybe in some workshop of everything, so that vibration would get transmitted from a machine to the floor, and then you could feel it, and it is a very like exhaustive for a person to keep feeling such kind of a vibration, because and it is anyways not good for human health also, that you are exposed to some kind of vibration every time. So it is better that vibration reduction techniques are used. Apart from that, they are also used for, like, for example, if I have a sensor that is being attached to a table or maybe a car which is used to measure its speed, but because of the vibration of the car it is not able to measure the exact speed of the car, then in that case the contact between the car and the sensor, it has some kind of a vibration reduction material like a rubber or a polymer, electroactive polymer, that tries to damp out the vibration and transfer only whatever the required information is. Okay, so it is very important that vibration reduction techniques are uh, studied and used. Then we had active and passive vibration absorbers. So your passive vibration absorbers were materials or your polymers or elastomers wherein the system characteristics were not changing with time. By this, what I mean is that its stiffness, its damping, and everything was not changing with time, and we were not able to change it. Like we once decided that okay, the mass, the spring stiffness, and the dashboard value should be this for the system, and we once applied it, it is going to be the same. Okay, and it may happen that it would be a good option for certain kind of behavior, but it may happen that if there is fluctuating load on the system, then these kind of a passive vibration absorbers would not work, right? In that case we would require active vibration absorber. In case of an active vibration absorber, we use active or smart materials like electroactive polymers, magnetorheological elastomers, or shape memory alloys, or these kind of materials. Now, these materials are smart materials because they deform or they show change of properties because of the external stimuli like your electric field, magnetic field, or temperature, and these things. Like, right? So the advantage of using active vibration absorber is because when you change the external stimuli, your vibration absorber is going to change its property, it is going to change its stiffness, or maybe it is going to change its damping value. So depending upon the kind of a vibration that you are having because of your system, you can change the characteristic of your active vibration absorber, and that would what help you to stabilize your system in a more efficient way. So generally, active vibration absorbers are used in case of what machines of like which have a very dynamic behavior. Like if you know that there is this car manufacturer Aston Martin, so they use this active vibration absorber. They have the shock absorbent. They use magnetorheological fluids because in that case, by changing the magnetic field, they change the damping property, and because of which your car becomes very shock absorbent. Okay. Then you have effect on vibration reduction of control and damping parameter. Okay, yes, this is in case of your passive vibration also and your active vibration also. That how with the change of control parameter and damping parameter, your vibration effect is being changed, right? Then we discussed about flexible nonlinear system. Essentially, we discussed about the cantilever beam. Then we discussed about the active cantilever beam and how your active cantilever beam, sorry, excited cantilever beam could be used as a piezoelectric energy harvesters. Because I gave you the example that what if you have a very windy day, so you use a cantilever beam, you apply a piezoelectric energy harvester on above it, and then because of the blowing of the wind, because of the movement and your piezoelectric material, since it shows both your piezoelectric effect and reverse piezoelectric effect, which means that on the if you apply deformation on it, it would produce charge on itself. So you could just store that charge or maybe just use that charge to do any kind of a work that you want to do. Similar is your case with the reverse piezoelectric effect that if you apply some voltage, it is going to produce some deformation. So that could also be used. Now, then we talked about the application of nonlinear dynamics. By applications, I mean your this flexible nonlinear system. Then you had your vibration absorbers. Then you had manufacturing processes like you had rolling and everything, which was nonlinear characteristic because as I told you that these like rolling and millings they produce chattering, right? Chattering means there are some kind of unwanted vibration that is inside the system experienced by the system because of maybe the tool wear or because of your not proper fixtures because your tool or maybe your workpiece is not fixed properly with the table, and because of that it vibrates when the tool comes in contact with the workpiece, or maybe your workpiece is a very like not it is having some kind of a uneven texture because of it your tool, if your tool is very sensitive, it may happen that the chattering could be produced, and this kind of chattering it leads to the excessive use of the energy, and it does not give you a proper finishing of the material, and it decreases the efficiency also. So it is better to avoid these kind of a chattering because there is no point, and anyway it is dangerous also. It is very dangerous because if your fixtures are not properly used, and if your workpiece of your or your this tool is not properly fixed, because of the vibration it may happen that it would just fly away and fall on someone. It could cause a very big loss, right? So it is very important that these kind of a chattering is avoided. And at last we discussed about chaos and its control, wherein we discussed about that why chaos is important to control, and by the control of chaos, we could just regulate it and make it go to a stable equilibrium state or the unstable equilibrium state, or we could just apply the tracking phenomenon on the chaos. Like I would define a trajectory and then my system would just follow that trajectory. If I want, like for a particular application, I want my system to just behave sinusoidally. So then I apply the control technique. Now I don't have to do anything. I just have to give a basic like model of the system, and then my control system, I have to give it the reference signal, and then my control system is just going to decide on itself that what should be the input that should be given to the system in order to get the proper response. Apart from that, by control, we were also doing synchronization, and by synchronization, I mean that with the variation of the initial condition, my system response was changing very much with time. But what if I want that my sensitivity towards the initial condition during chaos is reduced, and in that case, I apply synchronization. Or if I want my two systems to behave in a similar chaotic manner, then also I can use chaos. Apart from that, there is one more interesting application of chaos that I would like to share with you people, which is in the data encryption. So every one of you know about data encryption, which is being used worldwide nowadays. So that is also based on chaotic signal, do you know? Because if you have a chaotic signal, and then this Mohan also asked me about the Lyapunov exponent. So in case of chaos, when we are using it for data encryption, like chaotic signal, we try that our two or more Lyapunov exponents are positive, because in that case, if your data is encrypted, then this solving the data and then trying to find out that okay, what is actually embedded in that data, it becomes very difficult. If your system is more chaotic, because Lyapunov exponent is also a quantity that tells about that whether my system is less chaotic or more chaotic. It is very important that the behavior of the signal is very chaotic, so that it becomes very difficult for any kind of a hacker or for any kind of a third party to basically take out the information from the encrypted data. Okay, so I guess that is it from my side. Apart from that, MATLAB numerical simulation I have discussed a lot, and I guess you people can now deal with it. However, if you have any doubt, you can mail me at my email ID. And it was really good taking these sessions with you people. And with this, I would like to conclude this whole live session of mechanical vibration and sorry, nonlinear vibration. And I hope that you people enjoyed the course, and you must have got insights about how a physical system is being dealt with. And if you don't have any questions, we'll just end the session.
Madam, with respect to exam,
Yes.
uh, it will be like multiple option questions or how questions will be coming? Because
See,
I was expecting it is like paper exam, but it was
no. It is an online exam only. That I know, but whether it will be multiple option correct or MCQ, I don't know actually, because like I'm not into that team or anything. I also get tasks from them and I perform it. I'm also just like you. It's the only difference is that you come to study and I come to just explain. So I have no idea. But however, I think they must have given you the information about how the test is going to be, haven't they?
yeah, they told it will be mixer of questions.
Oh, but mostly it will be related to, like, it will be, I guess, your MCQs
Assignment.
only. Matlab MCQ types of, you'll get options, but I don't know whether only option is going to be correct or multiple options are going to be correct. So that I don't know. But I would suggest you that if you have this doubt, you can maybe just check it on their portal, or maybe you can search it on Google or YouTube. I guess then you'll get an answer for that. It will be
Oh,
helpful, I guess, for your preparation.
thank you very much, madam. Your explanations were good and it was very useful. Thank you.
Oh, thank you. That means a lot to me.
Thank you, madam. Thank you. Thank you.
Okay,
Actually, madam,
thank you.
all these 12, sorry, 13 sessions were very fabulous, and we learned a lot of things from your online sessions. And once again, thank you very much, madam.
Okay, thank you so much and all the best. And it was really good to teach you people, and it also helped me for in increasing my knowledge also. So thank you so much
Thank you.
and all the best. Okay,
Thank you. Thank you.
Thank
Thank
you,
you.
madam.
thank you.